Okay, so we're going to be working on lab number 20, which is mass defect and binding energy. Reading the pre-lab here, it says, a fundamental idea of modern nuclear chemistry is that mass and energy are equivalent. Mass can be changed into energy, and energy can be changed into mass. The equivalence of mass and energy seems to be responsible for the force that holds a nucleus together. Within each nucleus there are protons and neutrons. It seems that protons with their similar positive charges should repel each other and fly away from the nucleus, yet the protons remain held by some strong force. Scientists have observed that atoms have less mass than expected and that the missing mass is proportional to the force required to hold the particles in each nucleus together. The missing mass is called the mass defect, and the force that holds each nucleus together is called the nuclear binding energy. The equation E equals mc squared relates the quantities of mass and energy, where E is nuclear binding energy, m is the mass defect, and c is the speed of light. The relationship between mass and energy is also seen in nuclear reactions. Here, a small amount of mass is converted into a large amount of energy. Again, the equation E equals mc squared describes the relationship between the quantities of mass and energy. E is the energy released and m is the mass that is converted. So looking at the checkup questions, the first one asks, what are the proper units of energy, mass, and the speed of light in the equation E equals mc squared? Well, if you remember from either physical science or physics, energy is measured in joules. And a joule is a kilogram meter per second. So the units are energy is joules, mass is kilograms, and speed of light is meters per second. How will you determine the theoretical mass of an atom? What we're going to do is we are going to add the masses of all the protons, neutrons, and electrons contained in the atom. And how will you determine the actual mass of an atom? I have provided a link on my teacher page and grade link. You're going to use that link to find those values. So let's take a look at the procedure. It says, in this exercise, you will calculate the binding energy per nuclear particle for helium-4, iron-56, and uranium-232 atoms. You will need to make several preliminary calculations for each atom. Now, in these calculations, I want you to show your work, the labels, and the significant digits, the way they're to be rounded. So I will show you step by step how I want that to be done. The first step in the process is to calculate the theoretical mass of the atom. To do this, find the total mass of all the electrons, protons, and neutrons. Use the information that a proton is 1.0073 atomic mass units, a neutron is 1.0087 atomic mass units, and an electron is 0.00055 atomic mass units. For example, sodium-23 atoms have 11 protons, 11 electrons, and 12 neutrons. The theoretical mass of sodium-23 atom is 23.1908 atomic mass units. Only 4 decimal places are permitted based on significant digit rules. And they take you through the calculation on the next page, but I think if I walk you through it, it might help you understand that better. And I'm also going to show you how I want it written on your paper. So for sodium-23, the first thing we are going to find is the theoretical mass. You do not have to write these headings here, but I'm writing them so that when you go back through to do your calculations, you know exactly what you're finding. So to find the theoretical mass, I am going to use this notation for sodium. I'm going to write Na23. Now, down here, I want to find the atomic number from my periodic table, and when I look that up, it is 11. And so when I look at sodium, I know from the atomic number that it has 11 protons. The number of protons is the same as the number of electrons, so that is also 11. And to find the number of neutrons, I subtract the atomic number from the atomic mass. And so 23 minus 11 is 12 neutrons. So that's where they get those numbers from, just as a reminder. So then they're showing 11 protons. One proton has a mass of 1.0073 atomic mass units. And when I multiply 11 times that number, I get 11.0803 units. Now, in this case, I'm not going with the two significant digits here because these are pure numbers. It's a counted number. I'm going to go with keeping 4 decimal places. Okay, we're going to keep the number of decimal places. For the electrons, it's 11 electrons times 0.00055 over electrons, so that these cancel out. And when I do that multiplication, I get 0.00605 mass units. Keeping 1, 2, 3, 4, 5 decimal places. And for neutrons, it's 12 neutrons times 1.0087 units is 1 neutron. And when I multiply that, I get 12.1044 units. Then I add those all up. And when I add those all up, I get 23.1908 atomic mass units. Now remember, this has 5, but these two numbers have 4 decimal places. That's why I stick with 4 decimal places here. Okay. For number 2, this is where I write the actual mass. This is what you have to look up using the link that I have provided. They provide the actual mass for sodium-23 for you. It is 22. So this is step 2. You can use reference books to look up the actual masses of atoms. A reference source lists the mass of the sodium-23 atom as 22.9898 atomic mass units. So that is 22.9898 units. For 3, it says, to find the mass defect for an atom, subtract the actual mass from the theoretical mass. For the sodium-23 atom, the mass defect is 23.1908 minus 22.9898, or 0.2010 atomic mass units. So right here, I subtract this number. So 23.1908. I subtract 22.9898, which I have here. And when I do that, I get 0.2010 atomic mass units. So this is my mass defect. Should have put that as a label up there. But that is my mass defect that I just found. So it's subtracting my answer from 2 from my answer from 1. Okay. For step 4, this is where I find the mass defect in kilograms. I have to do a conversion to use it in E equals mc squared. So the conversion is, and they tell us here, convert the mass defect that is now in atomic mass units to units of kilograms. 1 atomic mass unit equals 1.66 times 10 to the negative 27th kilograms. The mass defect of sodium 23 atom is 3.34 times 10 to the negative 28 kilograms. So the way they do that is you take your answer from 3 and you do a conversion. And we know that 1 atomic mass unit is 1.66 times 10 to the negative 27th kilograms. When you multiply those two numbers together, you get 3.34 times 10 to the negative 28 kilograms, which is a very, very small number. I'm going to go on and use, well, I should be able to just get this on here. So to find our binding energy for number 5, it's E equals mc squared to find binding energy. So E equals our mass that we just found here, times the speed of light squared, and the speed of light is 3.0 times 10 to the 8th meters per second squared. So the binding energy, and I misspoke earlier, it's actually a joule is a kilogram meter squared per second squared. I misspoke when I said that earlier because we square this quantity. I forgot about that. So make sure you square this number. So on your calculator, what this will look like is I will enter 3, second EE here for me, 8, and I'm going to square that before I multiply it by this number, 3.34, second EE, negative 28, to get this number, 3.006 times 10 to the negative 11th. But because I have 3 significant digits here and here, I'm going to round that to 3 significant digits, so it will be 3.01 times 10 to the negative 11th joules. So this is my binding energy. And that was step 5 that I just showed. In step 6, they say to calculate the binding energy per nuclear particle by dividing the binding energy by the number of particles in the nucleus. The sodium-23 atom has 23 nuclear particles. Its binding energy per particle is, they took the answer from up here and divided it by the number of particles to get this. And I'm going to show you that right here. So for 6, this is the binding energy per particle. So I take my answer from 5, which is 3.01 times 10 to the negative 11 joules. And I divide it by 23 particles that are in the nucleus, or nucleons we also call them. When I do that, I get the answer 1.31, keeping 3 significant digits, times 10 to the negative 12 joules per particle. Now, I want to talk about this for a minute. Let's go back to just the binding energy. You might say, wow, that is a really small number. That is not a lot of energy at all. But remember, when we're talking about this energy, this is just one atom. And remember that in a mole of sodium, which would be about 23 grams, it would be 23 grams of this, so about 23 grams of sodium, you have 6.02 times 10 to the 23rd particles. So if we were to take 3.01 to the negative 11 and multiply that by 6.022 times 10 to the 23rd, we would end up with this number if we had a mole of sodium. And so this number is basically a 2 with 13 zeros after it. That is a lot of energy. That means that we're taking that 2 with the 13 zeros after it, and we are able to lift that mass a meter per second times a meter per second. Okay, so that is a tremendous amount of energy when you think of it that way, considering how many particles are in a mole. Okay, so I walked you through sodium. I'm also going to walk you through uranium. I'm going to take out some of these headings, but just so you see one more problem, and then I'm going to ask you to do the last two on your own. So for uranium 232, the first step, if I write this correctly, so uranium 232, I look it up on my periodic table, it has an atomic number of 92. So 92 means it has 92 protons. It has 92 electrons. And to find the neutrons, we subtract 92 from 232, which we get that it has 140 neutrons. So here I'm finding the theoretical mass from number 1. So this is 92 protons. Each proton has a mass of 1.0073 atomic mass units. When I multiply that out, I get 92.6716 atomic mass units. Now I'm going to highlight those numbers that are going to stay the same in all these calculations that you're going to use each time. So this number is not going to change. This will be the same every time we do it. Okay, 92 electrons. An electron has a mass of 0.00055 mass units. For 0.0506 atomic mass units. And again, this number here will stay the same for all of our calculations. 140 neutrons, 1 neutron, It's a mass of 1.0087 atomic mass units. Multiply that out, you get 141.218 atomic mass units for a grand total of 233.9402 mass units. Now for number 2, part of why I'm doing this with you is the actual mass that they have measured is 232.0372 mass units. So remember, you look this number up. For 3, I'm going to subtract 2 from 1. So 233.9402 mass units, 232.0372 mass units. When I subtract, I get 1.9030 mass units. So this is from 2 and this is from 1. For 4, I then take this number, which is my mass defect, and I convert it to kilograms, and 1 atomic mass unit is 1.66 times 10 to the negative 27th kilograms. So this again, this is one of those numbers that will be the same in all of my calculations. And when I multiply those together, I get 3.16 times 10 to the negative 7 kilograms. So that's my mass defect in kilograms. Number 5 is converting this to the binding energy, or calculating the binding energy, I should say. So E equals the mass in kilograms, 3.16 times 10 to the negative 27th kilograms, times the speed of light squared, this value will be the same each time as well. So when I do that multiplication, don't forget to square this number. So when I square this and multiply it by this number, I get 2.84 times 10 to the negative 10 joules. And remember, it looks like a very small number, but especially if we were to take a mole of this, which would be 232 grams, it's going to be a lot of energy when you multiply that by 6.02 times 10 to the 23rd. So this number came from 4. And then finally we calculate our binding energy per particle in the nucleus. So we take this number here, 2.84 times 10 to the negative 10 joules, and we divide it by the number of particles in the nucleus, which is the same as the mass number here. So we're going to divide that by 232 particles. And that equals 1.22 times 10 to the negative 12 joules per particle. And so I would then take all of those values and I would enter them into my data table here. Now notice they did not put any labels on these. You don't need to label the units because, the labels appear over here. So I would just transfer over my values, 233.9402. I already have my theoretical that I put in. My mass defect, 1.9030. My for my mass defect in kilograms, which is 3.16 times 10 to the negative 27. My binding energy, which is 2.84 times 10 to the negative 10. And then my binding energy per particle, which is 1.22 times 10 to the negative 12. Okay? And I want you to follow those steps and do the calculations for helium 4 and iron 56. So go ahead and do those calculations, and I will be back with another video to walk you through the graph a bit and a few of the answers.